to our webinar this week. And today we have our speaker, Xiaotao Yang from Purdue University. Actually, his opening slide introduced himself very well. And I'm not going to read it again, but I'm going to reiterate what I read from Xiaotao's website, that as seismologists that are very interested in working on the images from the subduction zones to the mountains, and for the mechanisms of the earthquake source to the various post-seismic disasters. So with that, I think Xiaotao today is going to mainly talk about the imaging work related to subduction zone as well as mountains, I think. And we're looking forward to the story that Xiaotao brought to us. So Xiaotao, please go ahead.
Okay. Thanks. Thanks to Zhangzhou for your invitation. So the first time when I heard the Earth's data program, I was thinking that this is exactly what we're doing. We all are doing here, to use the really big data to help us better understand the Earth in different aspects, using different techniques. But we all use some sort of data and certain skills using different computational nodes. So for myself, like this slide shows, I got my bachelor's degree from Chinese University of Purdue Sciences in Wuhan in 2008. And then I did my master's in University of Chinese Academy of Sciences, where Zhangzhou also went there. So we spent like three years there. And then I got my doctorate degree from Indiana University. I also did some postdoctoral research in University of Massachusetts Amherst and Harvard University before I came to Purdue University as an assistant professor in seismology. In my research, I want to know a lot about what do we know about the Earth, and what do we know about the Earth below the surface, the part that we cannot see from our eyes, but we have tools or geophysical tools that we can see. And for my research, my past projects, and my main focus is mostly on the lithosphere scale. And so we will try to understand the deformation or tectonics of lithosphere and the relationship with some geohazards. And the lithosphere is the outermost rigid layer here. This is showing a cartoon figure. Shows the different layers of the Earth, and the lithosphere is on top. It includes both the crust and could up to like 70, 80 kilometers, and also the mantle lithosphere, and a bit deeper than that. But in a whole, the lithosphere is relatively a rigid layer of the Earth. For my research, I focus on three main questions. One is like, how does the continental interior evolves? There are a lot of efforts or focuses have been basically put to continental margins or subduction zones. So which is also part of my research. But in addition to that, I'm also interested in continental interiors, and which is a little bit away from the margin, but I want to know how it evolves and what it tells us about the tectonic evolution of the Earth. And of course, the plate margins. And plate margins has both passive margins and active margins. And those different types of margins tell us really how the Earth, the lithosphere could evolve at different tectonic settings. And in a whole, how the Earth could evolve in the tectonic history, and what structure we could see from today, from present day structure. And in addition to the structural studies and tectonics, I'm also interested in earthquakes and volcanoes, and their relationship or the control form deep lithospheric structures. And with these three questions, or driven questions, my research is benefited from the use of high performance computing resources. So I combine the seismometers, like the waveform recordings from seismometers on the left, to combine that with high performance computing resources. And when we talk about high performance computing, I know you are all doing sort of that. So we use like thousands, even tens of thousands of CPU cores or some GPU cores to help us to understand, analyze and understand data, and to help us understand the scientific topics. For my research, I have been lucky enough to work on a series of projects that covers the different, really very diverse tectonic settings, all the way from subduction margins, including Alaska margin, Cascade margin, and also continental interiors. And mainly I have worked on Illinois Basin. I'm also currently working on a large-scale continental interior project. I also working on the Pacific margin, focused specifically on the Eastern North American Pacific margin, where I studied the Hartford Basin, which is the Pacific margin rift basin, and also the Adirondack Mountains, which is in intercratonic mountains in the opposite direction as the Illinois Basin. So there is an up and down part of the continent. So hopefully in the future, I could spread my research to other settings like the spreading center, or a combination of a different, or a transition of a different tectonic settings. That's also one of the interests I have. We have in this talk, I will highlight two of my passive projects. So one is on the Illinois Basin area in the central United States. And the second one will be focused on the Alaska margin. But this is a map that's not showing the real location of Alaska. It's actually somewhere into the northwest of the main North American continent. I will put a little bit more focus on the Alaska project, but I will go through a little bit about the Illinois Basin project to really get a spread or get a span of projects or structures, tectonics, all the way from the interior of the continent to subduction zones. And when we talk about continental interiors, like there are a large setting in China also. There is a North China Cretan or similar setting here in the central United States. And a lot of time when you look at that from a geographic map or topographic map, you will see a relatively flat interior. But that doesn't mean it's boring or it's simple. So actually, when you study the geologic records and tectonic records and the seismic structures, this area is actually much more complicated than we thought previously. And for this area, we peel out the top sediments or the Paleozoic sediments. And what we see is the depths of the Precambrian basement. So that means, this map shows the depths of the Precambrian basement, which shows really strong variation in the central United States. And when you look at the Illinois Basin from the surface with the sediments, you see a really flat cornfield or soybean field, all the places, or most of the places. But when you exclude the sediments, so what you see is a localized deep Precambrian basement. And this is right beneath the southeastern part of the Illinois Basin. So this is actually, this was a continental margin at sometime in late Cambrian or late Precambrian actually. But after that, there sediment deposition started and covered the structure. So there are before the sediment covers are earlier than Precambrian. And there are a lot of structure, a lot of tectonics going on at this location. But still, because it is within a continental interior setting, we're not quite sure about how it formed, how it evolved, and what happened to this area and the adjacent area. And when we talk the origin of the Illinois Basin, because as a basin, it is directly a low line or the subsidence within the interior of the continent. So we have basically three possible or potential mechanisms could explain the subsidence of the basin. One is horizontal stretching, which means you stretch the lithosphere horizontally and then you thin the lithosphere in the middle. And that could provide a condition space for sediments to deposit. The second possible mechanism is buckling. Instead of stretching, you actually squeeze or compress the lithosphere. By buckling the lithosphere, you also could create a subsidence at the surface. But the key difference between buckling and horizontal stretching is the thickness change of the lithosphere. In buckling, you will not thin the structure, or you will not thin the lithosphere. but you could just create a surface accommodation space. And the third mechanism, approximate mechanism, is gravitational sink. That means like the force is not from a horizontal direction. Instead, it may form a vertical pulling downward, form something like really you have a dense material that you keep pulling, keep pulling the lithosphere downward, and you could create a combination space at the surface. We want to use seismic tools to study or to at least narrow down which mechanism is more possible in this location, in this basin, to explain its formation. We use seismometers in the central United States here, and the red crosses are US array transport array stations and some other permanent stations here. And we use, those stations are approximately about 70 kilometers in spacing. We also use some higher density array in the southeastern part of the Illinois Basin area. Again, the red crosses are US array stations and other permanent stations. And the black triangles are our flexible array stations. This is by far the most dense and the largest scale flexible array network in central United States, if not in the whole US continent here. And here, I was involved a lot in this project to collect the data. We use the advanced tool and to understand the structure of the Earth below the basin. So I use the data I use is receiver functions. And receiver function means, for those of you who are not familiar with this, I want just to briefly go through what is a receiver function. So when you have an earthquake occurred, and the seismic energy travels to local structure and received by the seismometers here. So on this, like in the local scale, when you look at this cartoon, you have a wave traveling at this location. Then there is a direct wave travels the P wave and received by the station. There is also another wave that converted at this velocity interface. Interface means you have a velocity contrast across the interface. At this location, as the optical or the acoustic wave, it converts to different types of wave, S wave, here received by the seismometer as well. But S wave travels slower than P wave within this layer. And for a lot of times you see probably crustal structures here. But this could be multiple layers. This is an illustration of a one layer situation here. Because ice travels slower than P, it arrives later than direct P. So there's a time lag. And the value of the time lag is directly related to the velocity within this layer, or the more accurate, the velocity difference between P and ice in this layer. So we use this data, but we use the more advanced methods to image the structure. We use the full wave field plane wave migration method. It is kind of similar to the basically pre-stack depth migration in reflection seismology. So we have a wave front here, the wave propagates all the way to the local structure at the interface. Then it is scattered to multiple directions. The key difference between this method and the traditional common conversion point stack or CCP stacking method is the scattering. Here we use, or we take into account of the three-dimensional scattering of the energy from the image point. And CCP stack mainly considers the central array here to fully recover the scattered energy, and also to use all the waveforms received by other stations to better focus to this point. So when you have one array is relatively, you are not able to focus to a highly variable interface. But with more three-dimensional scattering data, you can better image this point. even at a situation you have a very rugged surface or a very high or strong variation of the velocity in the phase. So now we have this data, we apply the technique to migrate all the residual functions to depths. And after we have all the earthquake data, we stack them together after migration. And this is a cross-section on the left that shows one of the cross-section here from northwest to southeast across the Illinois basin. And the basically the wave here, the more like a black wave, shows the positive energies converted. And so we see there's a strong energy and coherent energy here, all the way going from 45 or so down to about 60 kilometers, and then shallows again to the southeast. But there's when you plot that in the map view, the color figure on the right shows the extracted depths of this layer. We interpret this to be the moho, moho surface here, or just say the moho. The blue column is deeper moho, and the red column is shallower moho. When you look at this map here, the white outline is the outline of the Illinois basin. And where we, like in this area to the central and western part of the Illinois basin, we have a very, very deep moho here. Now, this is really interesting, or this is a surprise observation. So we see this, but this is not at the place where we have the rift. Instead, it is away from the rift. So the thinning, the thickening of the crust here does not show any clear relationship or spatial relationship with the rifting that occurred here, where if you remember, we see very deep Precambrian basement here. We have thick sediments as well. So when you have a simplified version here, so we have a thick crust here and relatively shallow crust or thinner crust here and thick crust at this location. And this is the rift. And this is the major fault. This is called St. Genevieve fault. And across this fault, we have a big jump in terms of the crust thickness. All the way here, from about 40 to 45, all the way to 55, or even to 60 kilometers. And this is actually a highline within the Illinois basin. The Illinois basin as a whole is a lowline, but here is a Sparta shelf here. It's a highline within the basin. So that clearly shows a very super thick crust. And as you can see here, this is really a thick crust in this location. So there are I want to just highlight two key observations. One is, as I mentioned, like the crust is really thick here. In general, it is thick or thicker in the central and southeastern Illinois basin compared to other parts of the basin or the northern part of the basin. The second observation is, so when you look at a more detailed or finer scale or finer resolution image in the southern part of the Illinois basin, where we have the dense array, we're able to pick the localized thinning of the crust beneath the Rock Creek Graben. This Rock Creek Graben is connected to the rift. They are all rifting structures. And rifting structure happens when you pull the continent or pull the lithosphere apart. But this seems like it's a local, very localized structure. And it is far away from the thick crust we see further to the northwest here. Those are the two key observations I want you to remember. So from these two observations, I want to simply just briefly talk about our interpretation about the major hypothesis to explain the thickened crust and the localized thinning. So mainly we focus on the crust thickening here. There are a few, we listed here 5 potential hypotheses that could explain the thickened crust. And you could have a inherited thick crust, overthrusting, shortening here just shorten, you just compress that, but not overthrusting. Or you have relamination of the downgoing slab. There are some studies that propose there a very old fossilized slab that happens in the Precambrian time, which could have part of the upper crust that goes up and attached to the crust to form a thickened crust. So all of the process, those are possible. However, if you remember the thickened crust, it is relatively localized in Central and Southeastern North America and Southeastern Illinois Basin. So it's not all the way across or all the way along the old margin. And this is like the localization of this thickened crust basically could rule out a lot of those hypotheses, because all of these four hypotheses require more or less some along strike or along margin distribution of thicker crust, not localized thick crust. In addition, in this area, across all the Illinois Basin area, we have observed a lot of granite rhyolite events, like proposed events in Precambrian time. And this, with that information as well, we interpreted the magmatic underplating to be a more possible mechanism. So that means that with at the pre-Paleozoic, not Paleozoic, Precambrian time, and we have some magmatic events happening here, which attach some magma to the crust. Once the magma cooled down, it started to become more dense. And the denser part of the crust, or the underplated crust, it started to have or act as excess mass and to pull that down as the negative buoyancy force. So this is our interpretation, but so we did some simple, very simple 2D gravity modeling. So it's not a robust gravity modeling, just we want to figure out, do we need a high velocity or high density material in this place to explain the gravity and gravity observation or gravity data here. We have the observed data gravity anomaly, Boogie gravity anomaly is blue squares. And the orange crosses are calculated or predicted gravity anomaly with our models here. First, like if there's no underplating, but with a thickened crust, we have thickened crust, no underplating here. So we're not able to recover or predict the general pattern of the Boogie gravity anomaly. And in broad scale, in the Illinois Basin, we do see here, we go across this location and see a broad, higher Boogie gravity anomaly compared to the region outside of the basin. So now when we add a gravity, or add a density anomaly here, or high density anomaly, where to mimic the underplated lower crust, we do have a better fit. So this is simply saying that we need some high density material here to compensate and the Boogie gravity anomaly. However, this is a very, very simple 2D gravity modeling. So we have a student here and with the expert of doing gravity modeling in a more like 3D space. So we will proceed forward to see whether we could have a better understanding to narrow down the potential mechanism or explanation. Now to summarize that, for the Illinois Basin, which is the oval-shaped intracratonic basin, it is more likely, and there is a gravitational subsidence force instead of a marginal force that caused a thickening or subsidence at the surface. And then the strong deformation here and could occur and preserved within the continental interior. So the continental interior then serves as a very good place to study the Earth's long-term history. And for some part of the Earth, it could act as a place to tell us what the Earth could be in the future and after many, many years. Okay, so I have talked a lot about the interior Illinois Basin area here. Now I want to just pause for 5 seconds because we are going to switch the tectonic setting into Alaska. And when you drive from Inlet Basin to Alaska, it takes 10 or 20 hours. But now, if you want to just pause here, we can go there just in 5 seconds. Okay, we're now here. Let's go from a cratonic interior to a subduction margin. But before I go to on the project, I want to highlight a little bit. I want to talk a little bit about the general setting of subduction zones in case some of you want to know some basics about it. For subduction zones, we have a oceanic lithosphere that goes down and subducts below or beneath the continental lithosphere. Of course, the continental lithosphere has the continental crust part and the mantle part, like mantle lithosphere. And there are a few key locations or terms I want to point out here. One is this is a volcanic arc. So when you have slab subducts down, when it is deep enough and like 70 or 80, 100 kilometers, it started to release water into the overriding lithosphere or overriding mantle. And with more fluid or more water in the overriding mantle wedge, it started to, some rock on the mantle rock start to melt with the addition of water. And after melt, we have some partial melt accumulated in this location and then started to accumulate more and more and to form a magma reservoir and then erupt out. This is the volcanic arc. And then this is the far arc, and this the far arc is the seaward of the place, the part of the arc here. And this is the far arc across, and this is the mantle wedge. That means the mantle wedge is the wedge-shaped mantle lithosphere here, which serves as a very, very important part. This is the back arc cross or back arc location here. Okay, so we will use these terms when we study our projects. Okay. Now, when we talk about Alaska, this map shows the more or less real or closer to real location of Alaska. This is Alaska. We talk about Illinois Basin here. So in Alaska, and we also talk about Ring of Fire. The Ring of Fire is a series of volcanoes around the Pacific. In Alaska, the Aleutian Alaska subduction zone forms a large part of the Ring of Fire. So there are a lot of volcanoes distributed here. We also have a lot of earthquakes. And so when you look at this, we want to focus on what could we do to understand better about the subduction zone, the volcanoes, and potential earthquakes. So this is subduction zone that really a complicated subduction zone. So it's, subduction, we talk about the general setting in a more like really a simple version of a 2D version subduction setting. But in Alaska, it is very, very three-dimensional. We have the Pacific slab here subducting to the northwest below the Alaska continent. At the same time, we have a curved margin here. So it's not a straight margin. That matters a lot. We have a curved margin, the subduction could be very, very complicated. The deformation could be very complicated as well. We also have a smaller plate here. It's called a Yakta microplate. This microplate subducts also towards northwest below the Alaska. So you have further to the east, you have more like a transpressional margin here. You have transform boundary transpressional margin then to subduction of macroplate, subduction to a more or less a normal plate, subduction plate here. So you have a really complicated setting, and there is the major fault, the Denali fault here, and it really more or less parallel to the margin here. It's also curved. And here, as a complex subduction zone, we have a lot of earthquakes. And those earthquakes are distributed at different depths as you would expect to form a subduction zone. And there's also variation here. In blue or dark blue means deep earthquakes, and red color means shallow earthquakes. You have the shallow to deeper here, right like along the along perpendicular to the Pacific section of the subduction margin. And we look at here, and we go along the strike to the north and northeast, and there are less deeper earthquakes compared to this part, less dark blue colors here. But no, but when you go, still keep going to the central part of the subduction zone, and where we have the Denali, there's the Denali volcanic gap I will talk about later in the next slide. And we have, again, more deep earthquakes compared to this part. So you have more or less and more deeper earthquakes. And the general pattern from subduction zone earthquakes tell us the strong variation of the seismogenic property of the subduction interface or the subduction zone. In addition, when you look at the volcanoes in more detail, the red triangle is shown here. For the Aleutian section of the Aleutian the Alaska subduction zone, we have more or less like linear distributed volcanoes or arc volcanoes. And then we have a volcanic gap. It's also along the volcanic arc, but there's no volcanoes, no volcanic records here. And we also have some like the small volcanic features here. I call them Boulder Creek, Jama Dome volcanoes, and those Wrangell volcanic field to the northeast. And this, so you have three geographically grouped volcanoes: Aleutian arc volcanoes, the Central Alaska volcanoes, and the Wrangell volcanoes. And those two volcanoes, even though they are small, they are very important because they show this, they basically limit or outline the range or the span of the volcanic gap, the volcanoes gap and some volcanoes here. So there are two major questions I want to focus on. One is, what are the structural variations in terms of subducting slab and the overriding plate? And also, how or what can the structural variation tell us about the distribution of volcanoes? Those are the two questions that drive our research. And I use really another tool. So I use the residual function data for the Illinois Basin study. Now, I want to tell you a very cool study. I use a very cool tool. And this is a tool has been used widely a lot of studies. And we use ambient noise data or cross correlation for ambient noise data to image the lithospheric. So for ambient noise, like for any seismometer, so we show two seismometers, A and B. You have seismic waves all the time, 24/7. It records signals continuously. And you have earthquakes, but a lot or most of the time you do not have earthquakes. So instead, you have some wiggles recorded here. And those are the signals generated by some background noise, either local noise or for a field noise. It could be like a lot of time for ambient noise image, depends on the frequency you use. For our study, a lot of the energy are from the oceans. You have the Pacific Ocean to the south of Alaska, and you also have the Bering Sea to the west. All of those could produce some energy that could be recorded by the seismometers. And this by cross-correlating two wiggles at two stations, we're able to get a signal that shows the arrival of the similar waves or similar energy between the two wiggles. This is what we call the empirical Green's functions. Theoretically, we have noise sources distributed all around different azimuths. You would have a very good recovery of this signal here. So we use this data to run our more or less like surface wave tomography procedure. For this, we use advanced method. Advanced method means we take into account of more three-dimensional structure, and we could use the three-dimensional structure to compute the synthetic Green's functions. And this is the full wave simulation in 3D structure using finite difference scheme. Then we use the synthetic to compare that with observed Green's functions to find out the time difference, the arrival time difference. We mesh every waveform at multiple frequencies. And traditionally for surface or ambient noise tomography, and we use dispersion curves extracted from one virtual source to all the receivers by different methods. And in that way, you can definitely more or less you smooth out some information, but you're also not able to take into account of all the variations across individual waveforms. Here we use every waveform so we get from the empirical Green's functions. After measuring the arrival time differences, and we compute a finite frequency sensitivity kernel, 3D finite frequency kernel. Use this finite frequency kernel, we invert for the velocity perturbation that needed to compensate the difference, the travel time difference. This is an iterative process. We run this multiple times. Usually you can get a pretty converged structure within 4 or 5 iterations. Now with this method, we image the Aleutian Alaska margin in a very, very interesting details. So we'll talk about a lot of interesting structures. And we use the method, we use the data mainly from US-array TA stations and also some permanent networks as well, permanent and flexible stations. And after 5 iterations, this is what we get. We started from the reference model on the top at different depths. And then after 5 iterations, we improved the model a lot by better fitting the arrival time of the empirical Green's functions and by revealing more details. And more details or more useful details that could tell us something interesting about this margin and the volcanoes. So when we talk about big data, and this is a really large amount of data. And for the inversion, we also compute a matrix with like 10 to the 8th or 9th orders of the matrix. It's a super large matrix. And we use CPU, and in total, we use actually 150 CPU years. We need like thousands of CPUs that runs for many hours here. Okay, let's see whether it works to do that, right? So this is our model on top, and there are also some other models we compare here. In our paper, we compare more models as well. So like this is 2018 model, 2018, like 2 2018 models, and 2018 is the time when we started process our data and to really run through the process. Now, like we really first order observation, we review more details, and there are also some differences here. And even though we all see some high velocity here, like showing us a blue color, which means usually means slab, subducting slab. We see that in our model here, the slab is really more like better constrained in terms of the thickness and the strike and the variation of the direction. And there are also some structures here have 2 high velocity structure. I will mention a little more later, but this is a good comparison to highlight that. There are some high velocity here, but you're not able to associate that with some plate interface. More like there are like below the plate interface, but in a large scale, low resolution here. This is just one blob of velocity. Depending high velocity, depends on the resolution. So you don't always observe 2 separate high velocities. I will talk about later about why it matters. Okay, now let's talk about the structures, the key observations. There are a lot of information you can get from the velocity model, but I will not go through every details. I will only highlight a few observations, major observations. And first one, let's look at an 80 kilometers depth slice. Blue color means higher velocity, red color means lower shear wave velocity. There are 4 high velocity we interpret to be slab segments. There's 3 geographical areas. Aleutian southwestern Alaska area shown as the purple box, South Central Alaska in the red box, and Southeastern Alaska in black box. We have, if you remember, we have linear arc volcanoes, central volcanoes, and a volcanic gap, and Wrangell volcanoes. Excuse me. So we have 4 high velocity, one here. There are the second, third, and the 4th high velocity slab segments across the margin along the strike. We also have some back arc low velocities here, and just like northwest of or west of the Alaska or the Aleutian Southwest Alaska section. And we also build, like there's other structures when you go a little bit shallower, then we have 50 kilometers, basically is the depths that cross the Mantle Fault Arc. The Mantle Fault Arc serves as a very important structure or location, and to tell us something about the hydration status of the subduction zone, or even earthquake activities or McDonald's earthquakes. And for the 51 kilometers, we see low velocity here. The black line here is the plate interface. So this plate interface means that you have earthquakes here, subduction zone earthquakes. And so for velocities to the west here, that means they are above the plate. They are part of the mantle wedge or mantle fault arc. And below the curve, the black curve means you are actually within the subduction slab. So what I want to highlight here is the mantle fault arc here. So you see low velocities here, but you also see low velocity right below the volcanoes here. But you don't see clear low velocities below beneath the central part of the arc, the fault arc. So you see some fault arc of low velocities below the Wrangell volcanoes. Now going to even shallower, we're now at the crustal scale. At 28 kilometers, we want to see the crust. This black curve is the plate interface at 28 kilometers depth. We have the low velocity clearly shown here along the southwestern Alaska or Aleutian and southwestern Alaska section. Some low velocity here, and we have a lot of low velocity here below the Wrangell volcano. So again, those are the key observations. Now I want to show you 4 profiles across the 4 subduction slabs or high velocity slabs. And basically the profiles are all perpendicular to the strike. One, the southwestern Alaska here, central Alaska, we have 2 profiles because we have 2 high velocity slabs. And there's a slab across there's a profile across the Wrangell slab. Now I want to just focus on here. So now we have the Pacific, we have the Aleutian and southwestern Alaska where we have the Pacific slab subducting down below this Alaska continent here. And we have South Central Alaska here, the Yakutat plate, and the Yakutat segment, another segment here. And we have high velocity here. There is also a extremely high velocity below the Denali volcanic gap. We don't have volcanoes. And for all the locations where we have more or less some volcanoes, we all see some different scales of low velocities here. Low velocities are running below the Wrangell. The Wrangell also has very low velocity in the cross below the volcanoes. Those are the key observations. Now I want to show you a profile here, not profile, a 3D animation here. So we extract the velocity surfaces, isosurface. The blue color means velocity patches with velocities above 4.6, which we use to represent high velocity anomalies. Yellow patches or red patches means velocity lower than 4.1 kilometers per second. So there are a lot of features. I want you focus on future things. So you want to focus on the change of slab geometry. This is the slab, the high velocity slab. You want to focus on how it changes along the track. The translucent mesh here is a plate interface. So this, I want also, second one is I want you to focus on the four-arc low velocity above the plate interface. Then the other thing is to focus on the high velocity structure below the denoted volcanic gap here. Okay, I will pause talking for that while I play the animations. You have the gap here and the high velocity here. Okay, so because we don't have much time left, so I will pause the animation now. So there are what we observe, that we see high velocity structures along the ocean part and along the central Alaska, two high velocities and the Wrangell slab. And but the one question we want to ask is, what do they tell us about the segmentation of the slabs? So they are highly segmented, but whether they are physically separated or they're just continuously happening, but just with variation of strengths or other properties, that's basically a question one of them. And those are two observations in a member of the interpretations. One is the weak zones, and weak zones exist that connecting the high velocity slabs. The other is there are completely separated slab segments. And form earthquakes, and there are earthquakes that occurred a lot of times in Alaska. For the 1964 earthquake, magnitude 9.2 earthquake, it propagates mostly to the southwest, not to the northeast. And there are also structures when you look at tectonic tremors here. The tremors instead, different from the earthquakes, large earthquakes, the tremors only or mainly locates or occurs in the central part of the slab, central Alaska slabs, or above the Yakta slab segments. And you can also tell if there is a slight difference between distribution of tremors here and this location. If you remember, we observed two high velocity slabs, one here and the other here. So clearly, we show a strong segmentation. Really see segmentation of earthquakes and structures in this location, and also volcanoes later we'll talk about. And there are other observations I will not go through in detail. And from some of the preliminary data we know currently, there's the broken or the separated the interpretation of a separate slab is more preferred compared to the continuous slab. But there are more studies needed to understand this better. So I would go through quickly about later slides. So if you remember, the four arc low velocities and the variation of the low velocities. And there are multiple ways you can interpret the low velocities, but in this location, with the settings here, you have low velocity in the manual four arc here below the ocean arc. You also have low temperature here. With low velocity and low temperature, it is likely due to serpentinization in this location. And serpentinization means we have a lot of fluids accumulated in this location. And this is about 20 to 35% of serpentinization. So then serpentinization along the ocean arc, four arc is not something new. However, our observation really provides a clear, strong variation of the forearc hydration status or serpentinization status along the strike. We have low velocity here, not a central part, and part of the ocean. We have something part of the Rungo volcanoes or Rungo slab segments. So the strong variation is also important for us to understand the seismogenic properties and other hydration related properties in this location. Now the last question is volcanoes. So we have volcanoes at the Aleutian arc, where we have low velocity below the back arc and some low velocity below the cross here, where we interpret to be partial melt here. But when you go to the central part of the Alaska, where we have some like isolated two volcanic features, we also have some low velocity here. And when you go to the Wrangell volcanoes, we also have low velocity. It's again, but there's a clear, very strong low velocity within the cross below the Wrangell volcanoes, which we interpret to be partial melt. There are the low velocity column here may indicate either edge flow or just the upwelling of the mantle in the mantle wedge. So there are, this probably indicates there's a large crustal magma that exists here below the Wrangell volcanoes. So there is for the volcanic gap, in contrast, we don't see any low velocity in the mantle wedge, and we don't see any anomalies in the cross neither. So this probably indicates a relatively, like no matter what mechanism it is to explain the formation of this, it at least shows that there are, this is a dry and cold mantle wedge here compared to other places along the strike. So there is at least say that we don't see any signature for melt here, which could explain actually the lack of melt could explain the lack of volcanoes in this location. Now the last thing I want to review here is the two high velocity structures below central Alaska. So why it matters. So a lot of times when you talk about the lack of volcanoes here, we talk about flat subduction. But flat subduction occurs for both the two high velocity segments, for the whole Yakta segments. But we see some volcanoes here, but not here. So this variation or contrast in volcanism or in volcanic activity here do tell us something about the control of volcanoes other than just the subduction geometry or the slab. And we have some mantle wedge structures that could contribute to the distribution of volcanoes. Okay, now, so I know we're at the end. We only have 5 minutes into 10. So there is this is a summary that we see a strong variation of slabs and overriding structures along the Aleutian Alaska margin. And those strong variations explain the distribution of earthquakes and volcanic activities along this margin. So thank you. I will leave it this slide here, and I'm free to ask questions.
Okay, thank you very much, Xiaotao. And here's the first question in the chat. So Liang Yingwei from SUSTech is asking, how did you calculate the percentage of serpentinization? So yeah. Is it any calculation of the seismic velocity to the, I think that means the percentage of different minerals or in the subducted rocks. Okay, go ahead.
Yeah, I think that's a very good point. So I'm glad I have a backup slide to answer that question. So yes, to calculate the percentage of serpentinization, there are some studies. This is one of the studies to try to, this is definitely really based on some mineral physics studies or some experiments. So we have percentage of serpentinization here versus a velocity. So when you have a velocity at some values, we have a corresponding percentage of serpentinization. So there are definitely, you can also talk about like potential melt, but in this location, because we have a relatively low temperature, so melt is shouldn't be a potential magnetism for this location. So that's does that answer your question?
Okay, the next question from Chen Yingfeng from Zhejiang University. So it's a technical question. The seismic array is quite dense, as what 25 kilometer station spacing in Illinois basin. So he thinks that it's ideal for applying the migration image method. So have you compared with the migration image from the conventional method of the CCP, and how much resolution improvement you see there?
Yes, so one is we have, so we use a migration method. We use a forward migration here. I probably don't have the slides here, but we do have a clear improvement. So the key improvements is in the situation where you have strong variation of velocity interface. So when you, at this location, luckily, we do have a very strong variation of or of interface, like velocity interface out here. And this 3D scattering, this full wave field migration method, which is based on 3D scattering theory, does give us higher resolution to, we have a resolution test actually, but I don't have that in this, this presentation. So we have that like clear comparison that it does give us a better resolution for very rugged surface or highly varied velocity interface.
Okay, next question, please. Okay, I have a quick question. Maybe it's a comment. So to me, there are multiple ways to explain whether you have observed in terms of seismic velocity. So to include or exclude the melt model or melt-free model, I would like to see some evidence from electromagnetic observation. To me, that looks like the most effective way to include the absolute melt into the possible scenarios that you could discuss.
Yes, that's a very good point. So I did some calculation in our paper. I'm not showing that here. So for some of the melt here, not showing, not this melt, but yes. So for this place, for just the example here, we did some calculation here based on some scenarios to like there are velocity relationship between velocity and partial melt. So there is this is also something we want to know better in the future, because there are some parameters you need to constrain to get the melt calculated correctly. I think you also mentioned an MT study here. They could also help a lot. So for this location, we don't have MT studies yet, but that could potentially be a very good contribution, at least a comparison or cross-validation for our seismic model. That's a very good point. Thank you.
So more questions? Last question. Okay, I think the last question from Zhang Quan from Zhejiang University. So the resolution, the overall borehole depth map is different from zoom-in map in southern Illinois. So does this difference caused by different interpolating strategy?
Yes, so that's a very good point. So one is like the borehole map. This borehole map is from seismologists. But this is a paper like this basically led by a geologist and Stephen Marshak. Some of you probably heard him. So he used our borehole data, try to extract the first order observation, and also try to simplify the features, and to be more readable to geologists. So that's why they show different resolution. And so for if you are looking at this, if you are talking about this is the zoomed in, because we have a higher resolution image at this part where we have a denser array. If you remember, we have arrays like deployed in a denser solution here. This is a large scale, covers all the basin. Then in the southern part of the basin, we have the Oink array. Oink array has much denser, basically or smaller spacing compared to the other stations, which gives us a higher resolution. So when you look at the scale of the Rough Creek Graben, so it's only like less than 100 kilometers. With 70 kilometers spacing, you're not able to resolve that anything. So for this, like with the 70 kilometers, go back to the resolution between CCP compared to plane of migration. For the large scale, they show similar features. But when you have high resolution data, those two methods will be different a lot. So the plane of migration gives us a high resolution image about the Rough Creek Graben because we have good data coverage in this location. So that's what I hope that answers your question. Thank you.
Actually, there's another additional question probably you could answer before we finish our webinar today. So it's a technical question in terms of full waveform tomography. So based on the inversion velocity perturbation, so how do you update the velocity model?
Yes, so that's a good question. So when we have the velocity perturbation, so I'm trying to find where is my mouse. So, okay. Yeah, so we have a lot, it just, when you have a perturbation, you add back to the model you use to compute the synthetics. Then for the next iteration, you recompute the full wave simulation or recompute the synthetics with the updated model. So does that answer your question? But to get the velocity perturbation, this follows we use least square or LSQR method to do the inversion. So once you have the finite frequency kernel, the phase difference measurements, we do the inversion and get the velocity perturbation.
Okay, great. Thanks everyone for your participation, and thanks our speaker again, Xiaotao, for giving the talk. And next Wednesday we'll have Sarah speaking from Scripps Institution of Oceanography. So see you next week. Have a good evening and have a good day. Bye-bye.
Thank you. Bye.